I'm a motorhead. Long before I was a techie, I was a motorhead. I'm a third-generation motorhead. My grandfather bought a Cadillac touring car to take his 7 kids from Wisconsin to California in the 30s. My dad had a TR3. He had a Ford Mustang. My young single-digit years were with my brother. Our weekends were either spent in the garage or at the racetrack. We'd come home smelling like beer, cigarettes, and oil. They were the greatest days of my life. And you know what? This is why I love electric vehicles. They are so fast. They are so sophisticated. They have fewer moving parts. They can achieve great things that the gasoline vehicle can't. It's just the way to go. But there are lots of challenges ahead. And the challenge with EVs right now is they're too damn expensive. The average car in the U.S. is around $40,000 and the average EV is $62,000. That's not really accessible. So we need to bring the price down. And then people are worried about charging. How far can they go with their car? And how much is it going to cost them? You know, can they do it at home? Can they do it on the road? Which charging system do you use? Will the charger work? How long will it take? And then ultimately, what's my car going to be worth 5, 7, 8, 9, 10 years down the road? Is it going to be worth anything when the battery goes dead? Do I just throw it away like I do a flashlight that has, rechargeable batteries? It doesn't work anymore? Today we're talking to CEO Kedar Munipella, who leads TAE Power Solutions. They're focused on helping to make electric vehicles charge faster, run stronger, go farther, and last longer. I'm Jim McNeil, and this is Good Clean Energy. Hey, Kedar, welcome to Good Clean Energy.
Hey, thanks, Jim. It's great to be here.
I'm delighted to have you. There's so much stuff we want to talk about. And I was looking at things to talk about in regards to the state of the electric vehicle space. And there's so much going on around, kind of V to G, V to V, V to home, whether the electric vehicle infrastructure is going to be migrating and maturing so that people can have shared resources. And I just caught this Florida man quote that a guy powered his house during Hurricane Ian with his Ford F-150 Lightning truck. Did you see that?
Yeah, I actually read that. I mean, it's pretty amazing what he did. It was like 2 days that he went without any power and just lived off of that.
Yeah. So he was running his stove and his TV and his stereo and his fans and his cooktop, everything, for 2 days. And it took 20% of his battery.
That's amazing.
So, Kedar, you are the CEO of TAE Power Solutions. You know a whole lot about what's going on in the electric vehicle and stationary storage space. What I wanted to talk to you about is, what are the real challenges let's start with EV adoption in the world, and I guess in particular in the United States?
So, truly, I mean, this is an exciting time for not just EVs, but every form of electromobility. And if you think about what's really, I'll call it headwind to the adoption and increase in the presence of EVs, it really comes down to a few things. At the heart of it is the economics in terms of just cost versus an internal combustion engine and a cost relative to other modes of transportation. That's, I would argue, one of the biggest, if not the biggest challenges. Outside of that, you've got the infrastructure piece that acts as a barrier to adoption. For EVs, it's just not having enough charging infrastructure. And here again, if you compare with what an internal combustion engine does, which is a gas station pretty much around every corner, that's where we need to get to, and we're not there yet.
Right.
The other factor is just about things that you take for granted with technologies that have been around for a long time, which is reliability. And the last thing is just the basic choice, not having enough models, not having enough suppliers, just not having enough choices around EVs that you could go pick from.
Right.
So absent choices and not having adequate supply, or the economics not making quite as much sense as it will over the course of time, I think these are some of the challenges near term that we face. I don't see this as being a permanent headwind. I see all of these as challenges, but really opportunities for companies like us to be able to go fix and help accelerate this transition.
To your point, in terms of cost, I guess most people don't really fully appreciate that a battery is the most expensive component in an EV by 5 times more than what you'd usually pay for a powertrain, right?
Right.
So a $20,000 battery in a car versus a $4,000, powertrain, and that's kind of in the high-end luxury vehicle category. So like a Rover has a $5,000 engine and transmission, but the electric vehicle equivalent of that would have about $25,000 battery.
And the cost of the battery and the battery itself, that's really where I would say most of the focus, both around innovation and incremental improvements are. And to your point about 3 to 5x more expensive, the battery is really at the heart of the car. And arguably, as the most valuable part of the car, it should be the most expensive part. But does it have to be as expensive as it is today? Is it as optimized as it can be? I don't think so. And that's where you think about your first point about the adoption and you think about the cost. That's where most of the focus needs to be, both around reducing cost, improving supply or securing supply, and then improving performance. The more you can optimize for performance, I think the better the performance gets.
Well, most motorheads out there, myself included, will either enthusiastically or reluctantly agree that the performance of an electric vehicle is unlike anything they've ever experienced, right? I mean, you're getting cars that are going from 0 to 60 in under 3 seconds. You have the Silverado, which weighs 8,500 pounds, is 0 to 60 in 6 seconds. That's insane. So how are you going to make those cars more affordable?
Let's just talk about what's contributing to that cost first. And again, back to Silverado and that example about how heavy that car is. If you think about most of the cars with that level of towing capacity and with the ability to accelerate as quickly as those cars can, what you're talking about is the amount of power, which means bigger batteries. If you think about what that does is not just adding weight to your car, but adding cost to your car. What we do is fundamentally change the basic assumptions around how to derive power from the battery and how to do it more effectively. If you could get magically 15% more output from a battery, and by doing that, if you could reduce the size of your pack, which automatically reduces the weight in your cost, imagine what that does for your performance. That's fundamentally what we're going after. We're talking about optimizing the power that can be derived and then distributed from a battery. Doing all that by simplifying the complexity of what is a conventional powertrain for an EV vehicle. What we've done is disaggregated the battery by now controlling it at a module level versus a pack level. Gives you way more granularity, way more control. When you think about the two elements that matter most, state of charge, state of health, if you can control them dynamically and if you can control them real time, that's how you maximize the power and maximize the efficiency that you can derive from a battery pack. And that's fundamentally what we're working on.
And most people think of a battery as a single unit. It's a single entity, and most car companies deal with it that way, but it's actually multiple modules of cells. And in some cases, it's 10, sometimes it's 12 or 16 modules. And you deal with those modules individually, right?
Absolutely. So a traditional technology would treat your battery as a monolithic block. And when you treat it as a monolithic block, you pretty much have single points of failure and you have single points of control. What we've done is, in effect, disaggregated that. To your point, a pack has up to 36 modules. If you could control these 36 modules discretely, what you do is you can balance the load more effectively. What you can do is manage the temperatures more effectively. And that's what we've done. We've brought that granular control to an operation that fundamentally doesn't exist today. We're able to extend the range of a car. We're able to deliver more sustained output from a battery. The other thing that you didn't mention is we're also able to enable faster charging of the battery. That fundamentally addresses, in our minds, a high-value problem in the industry around charging infrastructure and the need to now spend as much time as you need charging your battery, we can reduce that charge time by anywhere from 50 to 75%, which is pretty dramatic.
So your thesis is by making the battery more efficient, you can either increase the power and the range of the vehicle, or you can reduce the cost by having a smaller battery.
That is correct.
Okay.
You could do both.
And when you talk about the components that are involved, I mean, there's a lot of components involved in an electric drivetrain, right? We have converters and inverters and transformers, and you guys have changed your parts count. Isn't that correct?
Dramatically. So we've gone from, just at the highest level, from 5 core modules in a powertrain, we've reduced that to 2 core modules. We now have just the battery and the inverter and the motor that drives the car. So fundamentally reduce the complexity and the number of elements needed to actually drive a powertrain, which is phenomenally different from anything that currently happens today.
So you've reduced the parts count, which is going to reduce cost, obviously, but you've also, at the same time, increased the reliability of the battery pack because you're dealing with each module discretely, right?
I mean, it's just amazing when you think about it that way. And it's counterintuitive. You're going from what's now relatively simple when you compare it to an internal combustion engine to something that's way more simpler in what we're doing. But that simplicity brings with it more granularity and actually brings with it more control. So you're doing something that's not just counterintuitive, but doing something that dramatically changes the performance of a vehicle, both in terms of cost and in terms of performance.
So how is it that TAE Power Solutions can charge a vehicle almost 75% faster?
It comes down to this fundamentally that benefits derived from the architecture that delivers all of the benefits we just spoke about. That granularity and that discrete ability to control at a module level versus a pack level allows you to pulse those modules, and that pulsing allows you to heat these modules from the inside out versus the outside in. So what that does is it reduces the amount of time you actually need to preheat these modules. One of the big challenges that you have is how do you do this without starting an electrochemical reaction? And the way that we've been able to do it and what's unique to us is these pulses that we can actually trigger that, probably not a scientific term, but tickles the electrons, which gets things started without really starting an electrochemical reaction. That allows you to heat it up while charging. And as you get to a certain temperature point, you're now at a steady state from a charge standpoint. And that charging now is on par as you would with any other fast charging. So you've cut out both at the front end and the back end the amount of time needed from preconditioning to actually charging a battery. And that's only possible based on the architecture that we've designed and developed with our ACI pack.
So for the non-Tesla listeners out there, they don't understand or know that batteries need to be at an optimal temperature to receive electrons in high current efficiently. And so what a Tesla will do is they'll say, hey, you're going to go supercharge your vehicle. I'm going to start heating it up.
Right.
I think it's about 20 minutes ahead of time, and it uses battery power to do that. In your case, you're getting to the optimal temperatures because you're dealing on a modular level, and then you're also doing something different. You're pulsing the current. So it's not just a steady state, high voltage, direct current charge. You're actually pulsing it, which allows you to control the impedance more carefully than the other direct charge, fast current stuff.
That's exactly what's happening. And again, Tesla's done a phenomenal job in that most of this is not visible to the driver. But for all of the other vehicles out there, this is actually a price that you've got to pay to go get your car charged. And that preconditioning step is actually pretty expensive from a time standpoint. And our ability to do away with it through this pulsing mechanism is something that's not just different, it's radically different.
The other thing that I think people care about, I mean, you're making things charge faster, which is great, but there's also speculation or even concern about the value of the vehicle long term. And the way you manage the battery is going to extend the life of that battery. Is that true?
True. By balancing the output and optimizing the performance of the battery, what you're doing is you're uniformly aging the battery. You're not stressing certain modules. What you also can do through this more discrete control that you have is when you're at a point when you need to either replace certain modules, you could actually do that. So you could extend the life of the whole pack by selectively replacing only certain modules that may be faulty for no fault of the operator, but could have issues with the manufacturing of the cells that went into the modules in the first place. Our technology allows us to do those swaps, which extends the life of the battery and increases the reliability of the car, which is really what you want to get to. And we haven't spoken about the second life of the battery itself, and we can talk about that in a second. But just the performance and the usage and the use patterns of the battery with our technology increases the overall life of the battery in its first life application. I think the economic equation changes dramatically if you could add, in this case, 10 to 20% extended life of your battery. And again, there's different ways to track how your battery is performing. You could have battery certificates and things of that nature. But as you do that, and as you think about the residual value and what remains of the battery, which, like you pointed out earlier, is the most valuable part of the car, if you can extend that life, you pretty much extend the value of the entire automotive. And when you think about the costs and you amortize that over the life of it, absolutely, the leasing costs come down, your affordability goes up. I suspect your insurance costs will start to come down too.
So, Kedar, how do we know all these things are true? I mean, are you installed in a vehicle or is this lab work?
We've done a lot of simulations. We've done a lot of data modeling. We've done a lot of digital twinning that's demonstrated all of these benefits and validated some of the use cases. What we're doing right now is taking all of the work that we've done in the virtual domain and translating that into the physical domain. We now already have a rig-based test stand where we've been able to turn a motor using our ACI pack, which is really the disaggregated inverter that powers your motor. By validating that and now starting to scale that up, we're in the process of proving that 10 to 15% overall improvement that we just spoke about. And early indicators and the data that we have gives us a lot of confidence that we're on track to either hit or exceed these numbers. Now, you don't want us to just work on this by ourselves and convince ourselves that everything's good. And we're very mindful of that. So we are working with external partners. We are working with tier one companies. We are working with other OEMs. And what we've done is set up an integrated development platform, which allows companies and partners to come work with us and develop this technology based on industry and real world requirements. So that way, there is no gaming of the system, so to speak. These benefits are against requirements that are industry standards, and not just industry standards of today, but where the industry is going to be in the next 3 to 5 years. And we're talking about disrupting it today and continuing that disruption over the course of that period of time.
Well, yeah, because this is really next generation technology. And to be clear, in terms of what you said, a digital twin is a copy of a physical machine. It's a digital copy of a physical machine. And you generate these twins, you do all your simulation. And now that you have a physical machine in the lab, are you verifying the numbers from your digital twin simulations and the physical machine?
We're absolutely doing that. We're actually taking it one step forward. We are starting to work with our partners to take our technology, put it on top of a battery, and actually run a physical vehicle with it. We expect to be doing that by the middle of next year, where you should be able to see an automotive on the road that's powered by our ACI technology. And ultimately, that's the proof that we want to be able to then go baseline, not just against a digital twin, but baseline against any other product that's out there and demonstrate that substantial improvement in performance and those benefit sets. So yes, to baselining and benchmarking against a digital twin, that's ongoing. But what we're more excited about is actually being able to look at a car or a bus or even a truck that runs on our ACI technology and all of these benefits that are delivered that can be measured and then can be tracked.
So we've been mostly talking about cars, consumer passenger vehicles, but there's obviously applications in, as you said, buses and trucks. So where's the blue ocean opportunity for your company?
It's a great question. For us, we're looking at everything that moves and everything that doesn't move. And honestly, everything out there is a disruptive opportunity for us. The big opportunity, of course, is in the passenger car vehicle market, which just by sheer volumes is a significant part of the market. But by no means is it the only part of the market. If you think about the early adopters, it's really going to be light commercial and middle or mid commercial vehicles, whether they be buses or trucks. You see the adoptions with municipalities and you look at where the buses are, that's probably going to happen first. But the size and scale of the opportunity as a percentage of the total market is going to be the same. It's the timing and the adoption that's going to look a little different. But over the course of the next 10 to 15 years, you expect all of them to be at that same level relative to their own size and scale. But that's just on the automotive side or the mobility side. If you think about the stationary side, there's a equally exciting opportunity that's unfolding in front of us, driven both by the transition to electric vehicles and the need for more energy and more electrons coming from there, but also the need for the infrastructure to support the transition from internal combustion engines to electric vehicles. When you think about all of the driving factors, a combination of growth by just sheer demand that's coming at us, growth driven by existential threats like climate change, and growth driven by policy factors that are meant to address both of the challenges that we face today, I see a lot of opportunity. So I wouldn't look at any one market as potentially blue ocean, but I'd look at all of the opportunities as one big, really big blue ocean.
Would it be a true statement to say that the larger commercial vehicle space is a little bit faster to market than the traditional passenger vehicle space?
That is true, and true for different reasons. True, one, because you're seeing that transition already playing out. A lot of the adoption in the LCV, HCV, or MCV market is likely going to happen first because of, one, the mandates, and second...
Can you unpack those acronyms for us?
Light commercial vehicles or mid to high commercial vehicles, just based on their weight class.
Right.
And you are seeing that faster than passenger cars. One, it's the risk averseness of the industry tends to be different for different weight classes of vehicles. But you are seeing the adoption much faster for commercial vehicles. And that's driven based on the use cases and based on the performance needs of those assets.
Well, you have municipalities that have net zero targets, and they're not going to get there if they don't change their public transportation methods, right?
Oh, absolutely. And when you think about the drivers between policy and, just consumer driven, in the commercial vehicle section, it's a combination of both. Policy playing a big role in the earlier adoption and the faster switch to electric vehicles. And we're seeing that. I mean, whether here in the US or in other parts of the world, you look at China as an example. Today, over 50% of all their commercial vehicles in urban areas are all electric. And I think the rest of the world's going to follow very quickly.
Well, from what I've been reading, it seems there's a great deal of interest in kind of a holistic home power solution. So if you do have a car with 100 kilowatts of power, that's substantially bigger than the average 14 kilowatt Tesla Powerwall, number one. You're going to need to have smarts to know when you're going to charge your vehicle, when your vehicle is going to be backup for your home, when your vehicle is going to give power back to the grid, and or incorporating that in your stationary storage technology. Is that all part of your roadmap?
It is. It absolutely is. I mean, so, you think about all the V2X, where X could be any one of the things you mentioned there.
Grid or home, right?
Grid or home could be all of that. And And it's also about how do you manage supply and demand from your energy storage system. So it's that algorithm and the ability to control that really is a distinguishing factor. It's the intelligence that we've built into our power system. So what we're doing is bringing that level of intelligence to manage how the electrons flow in or out and where and when they need to go based on different demand or need signals. It's almost a requirement that we've baked into our product development because we see this as an immediate need. And we see this as one of the things that as a consumer, you may not quite understand how that works, but you see the impact every time you look at your energy bills. And almost always people are surprised, in spite of having an energy storage system, why their bills are as high as they are. And that's something that we're looking at when you talk about peak shifting, when you talk about energy and power arbitrage. Those are fundamental requirements that our systems solve for.
So we can envision a future where a TAE Power Solutions home is connected to a TAE Power Solutions vehicle. Maybe you have solar on the roof, and you've got the smarts to know when the solar is going into the battery, when it's going into the house, when it's going into the grid, or when it's going into the car.
Power Solutions is all about electron management. That's what we want to get to. Our future is going to be about smart management of the electron.
Okay. So with that in mind, put on your future hat and tell me, what does a world look like filled with TAE Power Solutions products in the year 2035? What should we expect?
I would not just limit ourselves to TAE Power Solutions, but think about it from a holistic TAE standpoint. We're going to be in an ecosystem and in a universe where we'll probably be the only one, arguably, that not just generates electrons from a generation standpoint with our fusion technology. That's going to be powered by TAE Power Solutions, our power management systems there. We're going to be managing the distribution of those electrons across the value chain. And as we distribute it, we'll have the ability to store them, buffer them, and discharge them to different points that actually need them. As you migrate, and if you continue down that path on the journey with that electron, you'll find yourself on a vehicle, whether it's a two-wheeler, three-wheeler, or a four-wheeler, or a boat or an aeroplane, with sophisticated controls and technology that can extend the range of that mobility application. You're going to be able to do a lot different things than you would do today. So you'd be in a 2035 universe in an environment where TAE produces the electrons, manages the electrons, distributes the electrons, and consumes the electrons.
That's a great summary. And I guess it's probably important for us to point out that one of your customers is TAE Fusion Power, and one of the products you're going to be delivering are the power solutions to drive the next generation fusion reactor at TAE named Copernicus. And this is substantially different than what's been done before. So the systems you have were born of the need of TAE to deliver hundreds of megawatts of power in an instant, like in a millisecond. And you've taken that from the megawatt scale down to the kilowatt scale to power trucks, buses, trains, and cars. But we're now building a solution that's moving into, I think, a couple of gigawatts and maybe even 2.5 gigawatts.
So this is where we started. It was all about powering our fusion journey. We were born out of necessity as much as out of sheer innovation. And as we bridged that monumental divide between what was available off the grid and what our fusion reactor needed, what we developed were some of the most sophisticated, if not the most sophisticated, power management systems. And that's where we got our start. So TAE was our, I'll call it, first customer, arguably our most important customer as we strive towards a cleaner, greener future. And all of that scaling up that's happening on the fusion side is also driving the necessity for us to scale up. So as we do that, we're going to not just scale up in terms of the power that's needed. You referenced multiple gigawatts. We'll get there. But it's also the sophistication and the control that's needed to distribute that power to Today, we're distributing it to about 80,000 distinct points. As we continue to scale up, the number of points that we'll need to distribute that energy on a real-time basis is going to only grow. And for us to manage that efficiently and effectively is really going to be at the heart of our ability to continue to innovate and deliver our solutions for other high-power applications. So we've been able to scale up on the high-power applications, fusion being one of them. We've been able to scale down for automotive needs. We've been able to stay somewhere in between for other stationary needs. But that's the simplicity and the brilliance of our innovation, our ability to scale and the modularity of our technology. Fundamentally, it's those elements that go into our architecture and our innovation. And in that simplicity lies the sophistication that we've been able to deliver and prove.
Yeah, when I think about your technology, it kind of brings to mind, like an electron manifold, the ability to deliver electric power at different polarities or voltages to different devices from 12 volts to 12,000 volts to 120,000 volts in very short periods of time or longer periods of time. Right now at TAE, we draw power from the grid and we store it and then we drop it in an instant. And there's a direct need for that in building out the power charging grid for the United States, because a lot of these places that are not in metropolitan centers don't have access to a tremendous amount of power. And you have all these supercharger applications that need, 920 volts to deliver to a system. So I guess you're thinking about what it looks like if you draw power out in these remote areas and store it locally and then deliver pulse charging to vehicles. Is that also on the roadmap?
That's part of what we want to do, and that's part of our vision. And as we roll out our product set and our technology, that's definitely on our roadmap. And it's not just on our roadmap. I think it's aligned with where the industry and where this whole transition is going. So it's absolutely front and center of what we want to be working on and what we're focused on. The good news is it's aligned with the needs of the market, and it's aligned with absolute change that is necessary to enable this transformation.
Well, it's a very exciting vision, and Kedar, has been a very enlightening conversation. So thank you very much for joining us on Good Clean Energy.
Thank you, Jim. I really appreciated this.
When it comes down to summarizing this conversation with Kedar, I think the key word here is efficiency. It's using what you've got and making the most of it. And their approach to improve charging, get more power out of the battery, get longer life out of the battery, is going to make that battery more valuable, and it's going to make cars less expensive. There's a major transition taking place in the way we produce, distribute, store, and consume electrons. It's pretty clear to me that TAE Power Solutions is in the middle of it. Thank you for listening to Good Clean Energy.